Welcome to the Science of Hockey, the podcast where we break down the science behind ice hockey. I'm the analyst, your host, and every week we explore the data, research, and evidence that shape how we play, train, and understand the game of hockey. From biomechanics to performance psychology, we take you beyond the rink and into the research lab, giving you insights that go beyond hearsay and into what really makes the difference on the ice. Whether you're a player, a coach, a parent, or just someone passionate about the sport, we're here to bring you scientifically backed information in a language that's friendly and easy to understand. So grab your skates and let's dive into the science of hockey. Hello, hockey fans, and welcome back to the Science of Hockey. I'm the analyst, and today we're diving into the data behind one of the most critical skills on the ice: speed. We'll be discussing an article titled Testing Distance Characteristics and Reference Values for Ice Hockey Straight Sprint Speed and Acceleration, a systematic review and meta-analyses, published in Biology Sport. In this episode, we'll explore the findings from this extensive review, which analyzed data from numerous studies to establish reference values for sprint speed and acceleration across different distances in ice hockey. We'll break down what these results mean for players, coaches, and trainers looking to optimize performance in a sport where every millisecond counts. Whether you're focused on improving your own sprint or helping your team achieve peak acceleration, this episode is packed with valuable insights. So lace up your skates, and let's get into the science of sprinting on the ice.
All right, are you ready for this one?
I think so.
You sent us a whole bunch of research on hockey, but it's not about like the stuff you'd expect, like strategies or famous players.
Nope.
It's about the science behind skating.
Yeah, the science of how they move on the ice.
Exactly. Specifically, like how do we measure a hockey player's acceleration and their top speed?
And you know what turns out?
Yeah.
Scientists have some pretty specific recommendations about how to measure that stuff, and it's not what you'd think.
Okay. I am very intrigued. Lay it on me.
Okay, so get this. We're talking about a systematic review and meta-analysis from the journal Biology Sport.
Oh, wow. Okay, fancy.
I know, right? They went deep.
Yeah.
They looked at like over 60 studies
Wow.
with over 2,600 hockey players.
Oh my gosh, they were busy.
I know, to figure out how to measure these explosive movements on the ice.
Okay, 60 studies. That's a lot of research to dig through.
It is.
So what's the big takeaway here? Like, why does the distance they use even matter for measuring speed?
Well, think about it for a second.
Okay.
On a track, a sprinter can just go all out in a straight line.
Yeah.
But on the ice, you've got boards, you've got opponents, you've got constant changes in direction.
So much more dynamic.
Right. So figuring out like the ideal distance to measure acceleration and top speed
Yeah.
is key for really understanding what makes a player fast in an actual game.
Makes total sense. It's not just about raw speed.
Right.
It's about how that speed actually works in a game situation.
Exactly.
So what were researchers doing before that made things so complicated?
Well, it's funny, actually.
Yeah.
They were using all sorts of different distances for these sprint tests.
Really?
Yeah, some were using like 4 meters, some were using 20 meters, some were even just counting strides.
Oh, wow. So like
It was a total apples to oranges situation.
you couldn't really compare.
Exactly. You
Yeah.
couldn't compare players. You couldn't compare results from different studies.
It'd be like judging a race where everyone started at a different spot.
Exactly. It just made it really hard to figure out what actually makes a hockey player truly fast in a game.
So that's where this research comes in to try to create a standard.
Exactly.
Okay. So before we get into what they found for the ideal distances, can we back up for a sec?
Sure.
You mentioned biomechanics earlier.
Yeah.
What exactly does that mean when we talk about skating?
Right. Good point, because it's easy to think of skating as just running on ice.
I mean, it kind of?
Yeah, but the way our bodies move is actually totally different.
Okay.
Biomechanics is basically the study of how our bodies move.
Okay.
And in this case, it's all about understanding the specific movements and forces that are involved in skating.
So are you saying there's something about, like, the mechanics of skating that makes the distance of those tests even more important?
Absolutely. Because unlike running, skating involves gliding,
Right.
where you're basically coasting on the ice.
Yeah.
So the distance you're measuring over actually changes what you're capturing.
Oh, interesting.
So short distance, like really emphasize acceleration, that initial burst of power.
Right.
While longer distances are more about maintaining speed once you've hit that glide.
Interesting. So it sounds like figuring out the right distance is super crucial for isolating those specific skills.
It is.
And speaking of like the mechanics of skating, the research you sent even looked at how flared skate blades impact performance.
Oh, yeah, absolutely.
Which I thought was interesting.
Yeah, they're designed to maximize performance based on those unique biomechanics we were just talking about.
Very cool. I never realized there was so much science packed into a hockey skate.
Oh, yeah, tons.
So after all this analysis of different distances and skating mechanics, did the researchers figure out, like, what are the ideal distances for these tests?
They did.
Okay, great.
And the results were pretty clear-cut.
Awesome.
So when it comes to measuring that initial burst, that raw acceleration,
Yeah.
you want a short distance?
Oh, okay.
They found that 6.1 meters emerged as the sweet spot.
6.1 meters? I'm trying to picture that on the ice. Is that like the length of a face-off circle, or?
It's actually about 4 powerful strides for a hockey player.
Okay.
That's where you'd see those battles for the puck, those quick maneuvers to like dodge an opponent. It's all about that initial burst.
Okay, so 6.1 meters is for measuring that explosive first step. But what about top speed? Do you need a longer distance to figure that out?
You need a longer distance, but maybe not as much as you'd think.
Okay.
They found that 30 meters was the ideal distance to hit max velocity.
30 meters.
Yeah, it's long enough to reach their true top speed, but it's still relevant to a hockey game.
Okay, so 30 meters for top speed. That's fascinating. So are you saying that those long breakaway sprints we see down the entire ice aren't really the best measure of a player's true top speed?
Pretty much, yeah.
Yeah.
Players hit their max velocity by 30 meters.
Wow.
Testing any longer doesn't really tell you anything new.
So a scout or a coach who's looking at a player's speed over like 40 or 50 meters is actually looking at the wrong data.
It's not that it's wrong data,
Yeah.
but it might not be the full picture. What this research shows is that specific distances are better for measuring specific skills.
Okay.
If you want to see a player's acceleration, look at their 6.1 meter performance if you want top speed 30 meters.
So it's about using the data that actually matters for what you're trying to evaluate.
Exactly. And this applies to way more than just scouting and player evaluation.
Really? Like what?
This can totally change how we approach training, too.
Hold on. So you're telling me that coaches can use this info to design better training drills?
Absolutely.
Now I'm seeing how this goes way beyond just like measuring speed.
Right. Because imagine a coach designs drills specifically for those 6.1 meter bursts,
Okay.
focusing on explosiveness puck battles, or they create drills that target those 30-meter sprints so players can improve transitioning between zones or racing for loose pucks.
That's so cool.
It's amazing.
By understanding the ideal distances, you can tailor training to improve certain parts of a player's speed and performance. This is blowing my mind. I never thought the science behind hockey sprints could be this interesting.
Me neither.
I do have a question, though.
Okay, shoot.
You mentioned those 6.1 meter bursts being crucial for like puck battles and quick maneuvers. How often do those situations even happen in a real game?
That's a great question, and the research actually looked at that too.
Yep.
They found that players rely on those short bursts of acceleration for about 10% of the game.
10%? That's more than I would guessed.
It might seem small.
Yeah.
But think about all those moments where a tiny fraction of a second
Yeah.
makes all the difference. Face-offs, chasing a loose puck, battling along the boards.
Okay, yeah.
All those moments where that first step is huge.
Those short bursts might not make up a ton of the game, but they're happening at the most important moment.
Exactly. And that's why understanding these distances is so important.
Totally.
It helps us see the game in a whole new way and recognize those split-second moments where speed matters most.
Okay, yeah. This has been really eye-opening. I feel like I need to go back and rewatch some hockey games with this new knowledge.
You should.
But before we do that, I think we need to dig a little deeper into what all of this means, not just for hockey, but for other sports too.
Oh, for sure. This is just the start.
Yeah.
What we talked about today about hockey and those specific distances has the potential to change how we think about training and analyzing performance in all kinds of sports.
Okay, now I'm really hooked. I can't wait to see where this deep dive takes us next.
Me too.
So you're saying this research about specific distances and how those relate to different types of speed could be applied to other sports.
Yeah, totally.
I'm having a little trouble wrapping my head around that. How would that work?
Okay, so think about basketball for a second.
Okay.
Imagine a point guard driving to the basket.
Okay.
They need that explosive first step, that 6.1 meter burst to get past their defender.
Right.
And then to actually finish the play, they might need to accelerate over a longer distance, maybe closer to 30 meters to outrun the help defense.
Oh, okay. I see what you mean. So those same distances we talked about for hockey could be used to break down the different types of speed a basketball player needs.
Exactly. And it's not just basketball.
Hmm.
Take soccer, for example.
Okay.
A midfielder making a run might need a longer sprint, close to 30 meters, to get open for a pass.
Makes sense.
But a striker in the penalty box might rely more on those shorter bursts to create space for a shot.
I'm starting to see those distances play out in my head now for all kinds of sports. It's like a whole new way to analyze those explosive plays.
It is, and this knowledge can be super valuable for coaches and trainers.
Yeah, how so?
Well, they can use this to design drills that target those specific distances,
Okay.
helping athletes develop the exact type of speed they need for their sport.
So a soccer coach could have their midfielders focus on drills that build endurance and speed over longer distances.
Right.
And their strikers could work on quick bursts and agility.
Exactly. Tailoring their training to the demands of their position.
That's awesome. And this is where things get even more interesting, because it goes beyond just replicating those distances in training.
Right.
It's about understanding how the mechanics of movement change over different distances.
Mm-hmm.
I'm a little lost now. What do you mean by the mechanics of movement change?
Okay, so remember we talked about biomechanics earlier?
Yeah,
The way our bodies move changes depending on how far we're going.
right.
In those short bursts, it's all about power and acceleration.
Yeah.
You're using different muscles and generating force differently compared to when you're trying to maintain top speed over a longer distance.
Okay, so are you saying that coaches could use this knowledge to design drills that not only target specific distances, but also the specific biomechanics needed to excel at those distances?
Exactly. For example, a sprint coach working with a hockey player on those 6.1-meter bursts might focus on exercises that build explosiveness in the legs and core,
Oh, okay.
the muscles that generate that initial power.
Yeah.
But for 30-meter sprints, they might shift the focus to drills that improve stride length and efficiency.
Interesting. So it's not just about run faster, it's about understanding the nuances of speed and how they translate to different sports and different moments within a game.
You got it. It's about breaking those complex movements down into their core parts and then figuring out how to optimize each of them for better performance.
I've got to admit, I'm a little overwhelmed by all this info,
It's a lot.
but in a good way. It's making me want to go back and watch some of my favorite sporting events with this new perspective.
Yeah.
You know, pay attention to those distances and how they actually play out in real time.
I think you should.
Speaking of perspective, I'm curious about something.
Right.
We've been focusing a lot on straight line speed,
Yeah.
which makes sense for like track and field.
Mm-hmm.
But most sports involve tons of changes in direction, twists, turns, those split-second adjustments.
Totally.
How do researchers account for that?
That's a great question, and it's something researchers are really digging into right now.
Okay.
This research provides a really solid foundation for understanding straight line speed. But there's still a lot to learn about how these principles work with multi-directional movement.
It makes me think about agility and reaction time, you know?
Yeah.
Those split-second decisions
Yeah, those are huge.
that can make or break a play. It seems just as important as raw speed.
Oh, absolutely. And these areas are just begging for more research.
Yeah.
We're only just starting to figure out how our bodies move and how to optimize those movements for better performance.
So while this research has given us a lot of concrete answers about measuring speed,
Yeah.
it sounds like it's also opened up a whole new set of questions and possibilities.
Totally. And that's what makes science so cool. It's a never-ending journey of discovery.
Well, I'm feeling like we've uncovered a lot of really cool stuff on this deep dive into speed.
For sure.
But before we go too far down the rabbit hole, I think it's time to bring it back to our listener and leave them with something to think about.
Sounds good. Let's give them something to ponder.
All right, so we've talked about a lot here. From like the super technical stuff about measuring speed to how this all connects to training and understanding how we move in different sports.
Yeah, lots to cover.
But I think it's time to give our listeners something to really think about.
Okay, I've got something perfect for that.
Okay, hit me.
So remember those distances we were talking about?
Mm-hmm.
6.1 meters for acceleration and 30 meters for top speed,
Yeah, those were key.
and how those distances relate to straight line speed.
Right.
But remember, hockey isn't just about straight lines.
No way. Those players are all over the ice.
Right. It's like weaving through opponents, making those sharp turns, reacting to the play in like a split second.
So much happening all the time.
So here's what I want you to think about.
Okay.
How do you think those ideal distances might change when you're thinking about multi-directional movement?
Oh, that's a good question.
Like, how would you measure a player's ability to accelerate quickly to the left or right, or their top speed skating backwards?
I don't know. It makes me wonder if those distances would even work, or if you'd need totally new measurements for those complex moves.
Yeah, it's definitely a challenge, but that's where it gets exciting.
Yeah.
This research gives us a good starting point for understanding speed,
Yeah.
but it also opens up so many possibilities for studying those dynamic movements that happen all the time in sports.
It feels like we're just beginning to understand how our bodies move and how to use those movements for different situations in sports.
It's amazing. And as scientists keep looking into all of this,
Yeah.
we're going to find even more things that can change how we train and compete.
Well, you've definitely given us all a lot to think about. I know I'll never watch a hockey game the same way again.
Me neither. And it's not just hockey. It's any sport.
True. It's amazing how a little bit of science can change how we understand these athletes.
Yeah, totally.
So I think it's safe to say this deep dive into speed was a success.
Big time.
We learned about those specific distances for measuring acceleration and top speed, and how we can use that knowledge for training in all kinds of sports.
Right. And we even talked about what could be next for research in multidirectional movement.
So much cool stuff.
Yeah, it was an awesome journey.
So to wrap things up, we want to encourage you to keep thinking about all of this.
Keep those brains working.
The next time you watch a game, try to picture those 6.1-meter bursts and 30-meter sprints.
Yeah.
See how players use their speed in different situations and how those quick bursts or top speeds can change a play.
And if you're curious about any of this, don't be afraid to learn more about sports science.
Yes. There's so much to discover.
Absolutely.
As always, we love hearing your thoughts.
Yeah, hit us up.
And if you have any other topics you want us to deep dive into, let us know.
We're always looking for new adventures.
We'll see you next time as we keep exploring the world of knowledge.
Thanks for tuning in to the Science of Hockey. If you enjoyed today's episode, make sure to share it with your friends, teammates, or anyone who loves hockey as much as you do. Don't forget to subscribe so you never miss an episode. And we'd love to hear from you. Leave a comment to let us know what you liked, what you'd like to hear next, or any questions you have. Your feedback helps us make the show even better. Until next time, keep your skates sharp, your mind open, and keep chasing the science behind the game.